Hi, I'm Kathy C. from CUNY. Today I would like to talk about an untethered electro-pneumatic soft system for people with foot drop. Foot drop impairment affects a large population. It is responsible for compromised mobility and health. Current wearable devices are inadequate as they are rigid, uncomfortable, and expensive. To address this challenge, we developed a soft, lightweight, and affordable exosuit for ankle plantar flexion assistance. From this chart, we can see that the wearable devices are either too expensive or with restricted kinematics. On the other hand, our device has the advantage of being low cost of $65 and being lightweight of less than 4 pounds. Additionally, it can also generate a high force of about 300 newtons. Shown here is the design of our portable exosuit, which is compact and can be worn under a garment. It consists of a battery pack, a pneumatics controller, a vacuum pump, a pneumatic actuator known as an Origami actuator that we'll go further into details later, a set of IMUs that are mounted on each leg, and a foot switch. For the control architecture, essentially, the actuation system is comprised of two circuits. The electrical circuit supplying power to the components for operation and control, shown by the blue line, and the fluid circuit defining the path of airflow to the soft Origami actuator, shown by the gray arrow. The machine learning and sensors for gait assessment is very important for the control. We use IMUs and foot switches to detect the data and train the system so that it can estimate the gait of the subject to drive the pump. As such, the Origami actuator can provide plantar flexion assistance. Here is the fabrication of the vacuum-driven Origami actuator. The original actuator is made of a 3D printed skeleton wrapped by a nylon fabric and sealed. When the vacuum is applied, it contracts and exerts forces on its two attachment points. We conducted an experiment on the actuator itself where we used the Origami actuator to lift weight. On the right is the force pressure diagram. We also compared it with conventional pressure-driven actuator. The Origami actuator has the advantages of high power to weight ratio, being simple to manufacture, being inexpensive, and being user-friendly as a part of the wearable device. Now we'd like to talk about the working principle of the actuator. Contraction is mainly driven by the tension force of the nylon skin. Vacuuming the air from the actuator will temporarily decrease the internal pressure. This force is produced by the pressure difference between the internal and external fluids. Here shows the actuator providing plantar flexion assistance through contraction. On the right here shows the actuator contract when the heel strikes. Thanks to the independent operation of two solenoid valves, 4 configurations are possible. These configurations are shown here labeled A through D. A is before and during the heel strike, B is before and during toe off, C is during the stance phase, and D is during the swing phase. We conducted a test trial as shown in the figure. The subject can feel plantar flexion assistance when walking with a relatively stable gait, making our exosuit a success. We will continue our study on this project for further improvement. We would like to thank the National Science Foundation and the Grove School of Engineering at the City College of New York for supporting this project. Thank you for your time.